Look up at the night sky. What do you see? You see a tapestry of light woven from billions of stars and galaxies, each a magnificent island of matter adrift in the cosmic ocean. Think about the sheer scale of it all. There are colossal stars, millions of times larger than our own sun. There are swirling galaxies containing hundreds of billions of these stars, all held together by their immense weight. Even here on Earth, everything you can touch, from the ground beneath your feet to the air you breathe, has substance. It has weight. It has mass. But have you ever stopped to wonder why? Why does anything have mass at all? It's one of the most fundamental questions we can ask about the universe. For a long time, this was a profound puzzle for scientists. We had developed an incredibly successful picture of reality. We understood the tiny building blocks that make up everything we see. We knew about the forces that govern their interactions, from the light that travels across the cosmos to the energy that holds atoms together. But there was a glaring hole in our understanding. Our theories worked beautifully to describe the particles and forces, but they predicted that all these fundamental particles should be massless. They should all zip around the universe at the speed of light. Yet clearly they don't. You exist. You have mass. The Earth has mass. The stars have mass. This wasn't just a minor detail. It was a catastrophic failure in our description of nature. Without mass, the universe as we know it would be impossible. There would be no atoms because electrons would simply fly away from atomic nuclei at the speed of light. Without atoms, there would be no complex chemistry, no planets, no stars, and certainly no life. The universe would be a fleeting, ephemeral soup of particles, a thin and uninteresting cosmic broth. The fact that we are here, able to ponder this question, tells us that something must be giving these fundamental particles their substance, their very reality. The quest to find that something became one of the greatest scientific adventures of our time. So the stage was set for a grand mystery. On one side, we had the elegant equations that describe the universe's particles with stunning precision. On the other, we had the undeniable reality of a cosmos filled with substance and structure. The two didn't match. It was as if we had a perfect recipe for a cake, but it somehow came out of the oven weighing nothing. Something vital was missing from the ingredients list. Scientists knew they had to find this missing piece, not just to balance their equations, but to truly understand why the universe is not an empty, fleeting void, but a place of magnificent, enduring beauty. The answer would take us deep into the very fabric of space and time itself. To understand the mystery of mass, we first need to look at the rule book that governs the subatomic world. This rule book is called the Standard Model of Particle Physics. It is, without a doubt, one of the most successful scientific theories ever conceived. It's our best description of all the known elementary particles and the fundamental forces that control their behavior. Think of it as the ultimate recipe for the universe. It tells us what the fundamental ingredients are and how they mix together to form everything we see around us. It's a triumph of human curiosity, built on decades of brilliant experiments and theoretical insights from physicists all around the world. The Standard Model tells us that everything is made from a small number of elementary particles. The matter particles, the stuff you can touch, come in two main families, quarks and leptons. Quarks are the tiny particles that huddle together to build protons and neutrons, which form the heart of every atom. There are 6 types of quarks with whimsical names like up, down, charm, and strange. The other family, the leptons, includes the familiar electron, which orbits the atomic nucleus and is responsible for chemistry and electricity. So you, me, the Earth, and the most distant stars are all fundamentally made of just a few types of quarks and leptons. It's an astonishingly simple basis for such a complex universe. But particles are only half the story. The Standard Model also describes the forces that act between them. These forces are not just some mysterious action at a distance. They are carried by other particles called bosons. For example, the electromagnetic force, which holds atoms together and gives us light, is carried by a particle called the photon. When you see light, you are literally seeing a stream of photons traveling from a source to your eye. The strong nuclear force, which glues quarks together inside protons and neutrons, is carried by gluons. And the weak nuclear force, responsible for certain types of radioactive decay that power the sun, is carried by W and Z bosons. These bosons are the messengers of the universe. So we have a wonderfully complete picture. We have matter particles, quarks and leptons, and we have force-carrying particles, the bosons. The Standard Model describes how they all interact with incredible accuracy. Its predictions have been tested in countless experiments and have been found to be correct time and time again. But as we mentioned, there was that one enormous problem. The theory, in its purest form, demanded that all these particles be massless. The W and Z bosons, for instance, were known to be very heavy, almost 100 times heavier than a proton. The theory couldn't explain this. A vital component was missing from the model, a piece that would finally explain the origin of mass. The solution to the mass mystery is both beautifully simple and deeply strange. In the 1960s, a group of physicists, including Peter Higgs, proposed a radical new idea. They suggested that the entire universe, every single corner of it, is filled with an invisible energy field. You can't see it, you can't touch it, and you can't taste it, but it's there. It's everywhere. This energy field is now known as the Higgs field. It has been present since a fraction of a second after the Big Bang, and it permeates all of space like a kind of cosmic molasses or an invisible, silent ocean that occupies the entire vacuum of the cosmos. This field is what gives fundamental particles their mass. The idea is that as particles travel through space, they are actually traveling through this Higgs field. As they move, they interact with it. You can think of it like trying to walk through water. A person walking on a beach can move easily, but as soon as they step into the ocean, they feel a resistance. The water drags on them, making it harder to move. The Higgs field does something similar to particles. It drags on them, and this interaction, this resistance to being moved, is what we perceive as mass. The more strongly a particle interacts with the Higgs field, the more mass it has. This explains why different particles have different masses. Some particles, like the photon, which is the particle of light, don't interact with the Higgs field at all. They feel no drag. As a result, they have no mass and can travel at the ultimate cosmic speed limit, the speed of light. Other particles, like the electron, interact with the field only very slightly. This gives them a tiny amount of mass. Then there are particles like the top quark, the heaviest known elementary particle, which interact with the Higgs field very, very strongly. It's like trying to pull a giant boulder through a thick, sticky swamp. This intense interaction gives the top quark its enormous mass. So mass isn't something a particle has intrinsically. It's a property a particle acquires by virtue of its relationship with the universe around it. It is a measure of how much that particle couples to this all-pervading Higgs field. This was a revolutionary shift in our thinking. It meant that even the empty vacuum of space is not truly empty. It is filled with this incredible, invisible substance that gives reality its substance. The only thing left to do was to prove it. If this field existed, there had to be a way to detect it. Scientists knew that if they could just shake the field hard enough, they might be able to create a ripple in it, a particle. How do you prove that an invisible, all-pervading field exists? The answer lies in the strange rules of quantum mechanics. Just as the electromagnetic field can be excited to create a particle of light, a photon, the theory predicted that the Higgs field could also be excited. If you could pump enough energy into a single point in space, you could create a tiny, fleeting ripple in the field. This ripple, this quantum excitation, would manifest as a new particle, the Higgs boson. Finding this particle would be the definitive proof that the Higgs field was real. It would be the smoking gun that solved the mystery of mass. This was far easier said than done. The theory predicted that the Higgs boson would be incredibly massive itself, which meant it would take an enormous amount of energy to create one. It was also predicted to be extremely unstable, decaying into other, more familiar particles almost instantly after it was formed. You could never see a Higgs boson directly. Instead, you would have to search for the specific signature of particles it decayed into. It was like trying to prove a ghost had been in a room by looking for the faint footprints it left behind. This monumental task required building the most powerful machine ever constructed by humanity. That machine is the Large Hadron Collider, or LHC, at CERN on the border of France and Switzerland. The LHC is a 27-kilometer ring of superconducting magnets and accelerating structures buried 100 meters underground. Inside this ring, two beams of protons are accelerated to 99.9999991% of the speed of light. These beams are then smashed together at specific points, creating fireballs of pure energy in tiny subatomic explosions. For a fleeting moment, the conditions within these collisions mimic those of the very early universe, just a trillionth of a second after the Big Bang. The hope was that in some of these billions and billions of collisions, a Higgs boson would be forged from the raw energy. The search was one of the most difficult in the history of science. For every Higgs boson produced, trillions of other more mundane events occurred. Scientists had to sift through a mountain of data, an amount so vast it would fill millions of DVDs every single day. They were looking for a tiny, subtle bump in their graphs, a slight excess of certain decay products at a particular energy. It was a search for a needle in a continent-sized haystack. But after decades of planning, building and searching, on July 4, 2012, scientists at CERN announced to the world that they had finally found it. They had observed a new particle with the precise properties predicted for the Higgs boson. The ripple in the field had been detected. The discovery of the Higgs boson was a watershed moment for physics. It was the final triumphant confirmation of the standard model. The missing piece of the puzzle had been found, and it fit perfectly. It was a moment of profound intellectual satisfaction, the culmination of a half-century of theoretical and experimental work by thousands of scientists. The discovery wasn't just about finding another particle to add to the list. It was about confirming the existence of the Higgs field, the very mechanism that explains why the universe has substance. It solidified our entire understanding of the fundamental nature of reality. Without the Higgs field, our universe would be unrecognizable. Let's imagine for a moment a universe where this field never switched on after the Big Bang. All the fundamental particles, the quarks and the electrons, would be massless. Lacking mass, they would all travel at the speed of light. An electron, for example, would never be captured by a proton to form a hydrogen atom. It would simply zip past. Without atoms, there would be no possibility of forming the complex chemical structures needed for planets, stars, or life. The cosmos would be a thin, chaotic soup of particles, forever expanding and thinning out into nothingness. There would be no structure, no complexity, no us. The existence of the Higgs field is the reason we have a stable, structured, and interesting universe. It allows particles to slow down, to clump together, to form the atoms that are the building blocks of everything you see. It allows for the existence of the heavy W and Z bosons, which are crucial for the weak nuclear force. This force is essential for the process of nuclear fusion that powers our sun, the source of nearly all life and energy on Earth. So the Higgs field isn't some abstract, esoteric concept. It is a fundamental pillar of our existence. Its discovery validates the story of how our cosmos became a place capable of harboring life. This discovery resonates far beyond the laboratory. It represents a monumental achievement of human curiosity and collaboration. It required building the largest and most complex scientific instrument in history, bringing together nations from across the globe in a shared quest for knowledge. The discovery of the Higgs boson is a powerful reminder that we, a species confined to a small rocky planet, are capable of probing the deepest secrets of the cosmos. We can ask the grandest of questions. Why are we here? Why is there something rather than nothing? And through science, we can begin to find the answers. It's a testament to what we can achieve when we work together to explore the unknown. Finding the Higgs boson was a monumental achievement, but in science, every answer seems to open up a new, even more profound set of questions. The completion of the Standard Model was not the end of physics, it was the end of a chapter. It gives us a solid foundation, a verified map of the territory we understand. But it also highlights the vast uncharted wilderness that lies beyond. The Higgs boson itself is a mysterious particle. Why does it have the mass that it does? Could there be more than one type of Higgs boson? The Standard Model doesn't answer these questions, telling us that our journey into understanding the universe is far from over. One of the biggest remaining mysteries is gravity. The Standard Model brilliantly describes 3 of the 4 fundamental forces of nature, but gravity is left out in the cold. We have Einstein's theory of general relativity, which describes gravity as the curvature of space-time, but it doesn't fit with the quantum rules of the Standard Model. Physicists are searching for a quantum theory of gravity, a theory of everything that would unite all the forces of nature into a single, elegant framework. The Higgs boson might be a window into this new physics. Studying its properties with even greater precision could reveal subtle clues about how it might interact with whatever particle carries the force of gravity. Then there is the puzzle of the dark universe. All the particles in the Standard Model, the quarks, leptons and bosons, including the Higgs, make up only about 5% of the total energy and matter in the cosmos. The other 95% is a complete mystery. About 27% is thought to be dark matter, an invisible substance whose gravity holds galaxies together. The remaining 68% is dark energy, a strange repulsive force that is causing the expansion of the universe to accelerate. The Standard Model has nothing to say about these dominant components of our universe. Are there new particles and new fields out there waiting to be discovered? Perhaps the Higgs boson interacts with this dark sector in ways we don't yet understand. The discovery of the Higgs boson is therefore not an end but a beginning. It is a tool, a new lamp with which we can illuminate the dark corners of the cosmos. By continuing to study it at the LHC and future colliders, we hope to find cracks in the Standard Model that point the way toward a deeper, more complete theory. This is the nature of science. It is a continuous, thrilling adventure that pushes the boundaries of human knowledge ever outward. We have answered the ancient question of mass, but in doing so we have unveiled an even grander vista of mysteries. The universe is far stranger and more wonderful than we ever imagined, and the quest to understand it has only just begun.